arrow mark is into a symbol, that is a photodiode. Arrow marks are from the symbol, that is nothing but light emitting diode. Now, photodiodes are semiconductor light sensors that generate a current or voltage when the PN junction in the semiconductor is illuminated by the light. Now, whenever light is falling on the PN junction, now due to that light, now these charge carriers will acquire some energy so that the electron or hole movement will take place from P region to N region. That means the current or voltage is going to be generated with the help of your light fall. Okay. Now these are semiconductor light sensors that generate a current or voltage when the PN junction in the semiconductor is illuminated by light. Whenever some light is falling on the junction, due to that light, and now there will be a generation of current or voltage. Now, when a photon of sufficient energy, which strikes the diode, it excites an electron, thereby creating a free electron, and it's the same thing for the hole also. This mechanism is called as photoelectric effect. I think you people are already heard the photoelectric effect. Okay, now the same thing here also. Okay, now what is the what is here meaning inner photoelectric effect? When a photon of sufficient energy which strikes the diode, whenever a photon of energy is falling, which is striking the diode, it excites an electron, thereby creating a free electron, which is the same for the holes also. Now this mechanism is called inner photoelectric effect. Now this device can be used in 3 modes. The photodiode can be used in 3 modes. The first mode is a photovoltaic mode, which is usually as the solar cells. Whatever the solar cells nowadays you people are seeing, there the mechanism is the photovoltaic mechanism. The first mode of operation of photodiode is photovoltaic cell as a solar cell. Second one is reverse bias as a photodetector. Third one is a forward bias as an LED. Now, if you are operating this photodiode, this device in the forward bias, that is a light emitting diode. If you are operating in the reverse bias, that is your photodetector. Application is photodetector. Now, the first one is a photovoltaic. That is also one type of operation. These 3 modes we are going to see today. That is a photodiode. Once again, a photodiode is a type of photodetector capable of, remember this is very, very important thing, converting light energy into electrical energy. Because whenever light is falling on the PN junction diode, due to that light, the current or voltage generation will take place. Now what is happening? Light is converting into electrical energy. Now the diode which is capable of converting light energy to the electrical energy, that diode is nothing but your photodiode. Now one more diode is there, light emitting diode. What is that light emitting diode? Converting light energy into electrical energy. That we will see in the later slides. Now photodiodes are similar to the regular semiconductor diode. Now photodiode is exactly equivalent to your PN junction diode only, except that they may either exposed to detect UV or X-rays or packaged with a window of optical fiber to allow light to reach a sensitive part of the device. Now the difference between PN junction diode as well as this photodiode is it is used to detect the X-rays. This is a only constructional feature is different. In case of PN junction diode, P-type material, N-type material you are combining so that it is forming as a PN junction. But photodiode, we are calling it is nothing but a PN junction diode, but the construction of this is different. Due to the difference in construction, now it is acting as a special feature. Now a photodiode is designed to operate in reverse bias only. In this slide, 2 important points are there. One is a photodiode is a type of photodetector. What it will do, it can convert light energy into your electrical energy. And the second thing, photodiode is designed to operate in which bias? That is in reverse bias only. Now in the last class also we have seen GNR diode is also is operating in reverse bias. Tunnel diode is also, it is normally in the forward and reverse. During the forward tunnel current, along with the tunnel current, diffusion current is going to occur. And now this photodiode, it is operating in your reverse bias. Okay, next light emitting diode, LED is that is going to operate in forward bias. Just remember the things. In which direction we are going to operate the device to achieve our actual property. Now, the materials the commonly used to produce the photodiodes, generally these are the materials they are using. These wavelengths are very, very important. Remember this. The first one is silicon material. For the silicon material, the electromagnetic wavelength, spectrum wavelength will be 190 nanometer to 1110 nanometer. This is the spectrum wavelength for the silicon. During with this range only, it will act as the photodetector or the photodiode. Beyond this, the silicon device, it will not act as your photodiode. Now, for the germanium device, what is the wavelength range? 400 nanometer to 1700 nanometer. Indium gallium arsenide, which is one type of material. For this material, 800 to 2600. Now, lead sulfide, it is 100 to 3500 nanometers. Now, remember this wavelength for the different types of materials. But try to remember only these two materials, silicon and germanium, because our basic semiconductors are silicon as well as the germanium materials. Now, what are the different types of photodiodes? Now, there are different, depending upon the construction, based on its construction, photodiodes can be classified into PN photodiode, Schottky photodiode, PIN photodiode, avalanche photodiode. But these four photodiodes we are not at all discussing. Just if it is asking in a 2 marks question in the external examination, now how many ways photodiodes are classified means they are classified into 4 ways. Now, for that purpose only, I kept this slide here. 4 types is, first one is PN photodiode, second one is Schottky photodiode, third one is PIN photodiode, fourth one is avalanche photodiode. Right, now this is the construction of our photodiode. Now, basically photodiode is nothing but your PN junction diode. Now, where are this P-type material and N-type material and extra materials we are using to construct a photodiode? Now, see, this is a cross-section of your silicon photodiode. Now, this is a bulk N-type silicon. This is nothing but your N-type material. Now, this portion is nothing but your P-type material. See, this is P active area. This is your P active area. This small area, this area is P active area. And this is your N-type, very bulk, a huge amount of N is there. Whenever P-type material, N-type material is there, there is a formation of depletion region. Now, this region we are calling as your depletion region. Now, that's why this is a P and this is your N junction. This is simple PN junction. But the construction is different. Now, it has a silicon nitride passive air coating is there, diffusion mask is there. Now, it has a back metallization cathode and the back contact diffusion. All these things are not necessary for you. Just see the construction of the photodiode. And now, it is like a simple PN junction diode. It has an anode part. This is your anode and this is nothing but your cathode. Okay, now this is your P-type material and this is your N-type material. Now, draw the same diagram when he asks in the external examination. It is a construction of your photodiode. See, this is the same diagram I kept here also for easy understanding. The N-type silicon is a starting material. This is N-type silicon is a starting material for us. A thin P layer is formed on the front surface of the device. A thin, very small, thin P layer is formed on the front surface of the device by this is a process, thermal diffusion or ion implantation. With this process only, we can form the P region as well as N region. I think this people are going to see in VLSA subject, that is in later classes. And now, with the help of the diffusion process or ion implantation process, you can form the P region as well as the N regions. Now, the interface between P layer and N silicon is known as the PN junction. Now, this is a P layer and this is your N layer, this is N material. The interface between these two, this is nothing but your PN junction. A small metal contacts are applied to the front surface to the device. It is a metal contact. This metal contact is, it is an anode. To connect to the outside wall, it is a metal contact is given. And backside also one more metal contact is given. This complete black one is nothing but your metal contact. This is your cathode. This is a cathode and this is your anode part. The back contact is the cathode and the front contact is the anode. The active area coated with either silicon nitride or silicon monoxide or silicon oxide for the protection and to serve as anti-reflective coating. Now, what is the purpose of silicon nitride and what is all those things? It will be to protect the device Now this we can see for the later classes. Okay, the thickness of this coating is optimized for particular irradiation wavelengths. What is the thickness of this? It is given by the particular wavelengths. Now what is the wavelength of the device, which material you are selecting? That is depending upon the particular wavelengths. Right. And now we will see the operation of the PN photodiode. At the PN junction, there will be a concentration gradient that causes electron to diffuse into P layer and the holes to diffuse into the N layer. Now, ultimately, see the previous slide. Now, from this previous slide, in the P region, majority charge carriers are holes. The N region, majority charge carriers of electrons. Here, less number of electrons are there. Here, more number of electrons are there in N region. Here, more number of holes are there in P region. Here, less number of holes are there in N region. Due to the concentration gradient, the diffusion of the charge carriers will take place. Now, this diffusion results in opposing electrical potential, often referred to as internal bias. Now, that is we are calling as the internal bias. In a general PN junction diode, light enters the device through the thin P layer. Absorption causes, what will cause the absorption? Now, this absorption will causes the light intensity to drop exponentially with the penetration depth. Now, how much light particles are penetrated? Now, according to that, now this current generation is also going to be depends. Any photons absorbed in the depletion region, they will produce the charge carrier that are immediately separate in natural internal bias. Eventually, there will be the movement of charge carriers. Okay, now this is the basic operation. The main thing is this is the thing. Now, light intensity, how much intensity of light it is falling on the PN junction, according to that, it will penetrate into the very depth of your depletion region. Now, these photon, what will they will do? Any photon absorbed in the depletion region, they will produce the charge carriers that are immediately separated and stepped across the junction by the internal bias. Eventually, there will be the movement of free charge carriers. Now, due to the movement of charge carriers, ultimately the current flow will take place. This is the basic operation of your photodiode. Now, see the working principle. Right. Okay. Now, what is the working of your photodiode? Now, see the same thing here. Now, this is a P type and this is a N type. Now, take a simple material point of view. Okay. Now, incident of photons. Now, the light is falling in the PN junction. Now, this is a depletion region of these two things. Okay, this is a depletion region. When the light is falling in the PN junction, now what is going to happen? Due to this photon energy, now immediately it will generate some free carriers. Now, these free carriers, they will move through the junction to the P to the N type, or they will move from the N to the P type. Because of movement of these electrons and holes, the current conduction will take place. Now, this is the simple working of photodiode. The only adding parameter here is the photon. Now, we are going to illuminate the light on the PN junction. Now, due to this light, the photon energy, now the free carriers will be generated in the depletion region movement of these charge carriers will cause the current flow. In case of this diode, photodiode. Now, what is the working of a photodiode? When a photon of ample energy which strikes the diode, now what it will do? It makes a couple of an electron hole pair. Okay, this mechanism is called the inner photoelectric effect. Now, if the absorption arises in the depletion junction, now then the carriers are moved from junction by inbuilt electric field in the depletion region. Now, whenever due to this light, if any free carriers are generated in the depletion region, that will be moved, that will be removed from the depletion region, in the sense that will move to the P region, or that will move to the N region. Due to that, the current conduction will be takes place. Now, the holes in the region will move towards the anode and the electrons will move towards the cathode. Now, in the sense, anode is nothing but your P-type and the cathode is nothing but N-type. Ultimately, the holes will move to the P-type region, and at the same time, electrons will move from the N-type to the P-type. Now, this is the movement of your electrons and holes. The entire current through the diode is sum of absence of light and the photocurrent. Now, so absence of light, how much barrier potential is there, how much current is there, that is plus. Now, in presence of light, how much current is there, that is the complete current you have. Now, so the absent current must be reduced to maximum the sensitivity of the device. That means in absence of light, if current is there, ultimately that current is added to the basic light current. Now, if absence of the light, if it is zero current is there, the complete current is due to the light current. For us, now the absent current must be reduced to the maximum extent. That means it must be reduced to the zero, so that the maximum current we can achieve with the help of the light current. Okay, going to happen. Now, what are the different types of these modes of operation? Just now I discussed. There are three modes of operation. We are having photovoltaic mode, photoconductive mode, as well as the avalanche diode mode. And now the photovoltaic mode. What is this photovoltaic mode? See, the very important thing. This mode is also known as the zero bias mode. If you are not applying any bias, zero bias mode, you are calling as your photovoltaic mode, in which a voltage is produced by the light and photodiode. Under the zero bias, the complete voltage is produced by the light and photodiode. How much light it is falling in the PN junction, the complete voltage is produced because of this light only. This is in photovoltaic mode. The best example is nothing but a solar cell. Now, in the solar cell, now if in a voltage or some energy is stored, that is due to the illumination of light on the solar panel. Now, that's why what is photovoltaic mode? This mode is also known as your zero bias mode. Now, in which a voltage is produced by light and photodiode. Now, how much light it is falling on the PN junction? Because of that, the generated voltage, that is nothing but this is a maximum voltage in the photovoltaic mode. Now, it gives a very small dynamic range and non-linear necessity of the voltage form. Now, this in case of photovoltaic mode. Now, what is the photoconductive mode? Second type of mode is photoconductive mode. The photodiodes used in the photoconductive mode is more usually reverse bias. Now, see, the first one is the photovoltaic mode. Now, see, this is photovoltaic mode. It is neither forward bias or nor in reverse bias. It is under zero bias mode. Under zero bias mode, now the voltage that is developed, that is completely due to the light end of photodiode. How much light is falling on the PN junction. Now, zero bias mode is a photovoltaic mode. What is photoconductive mode? When it is in reverse bias. When this junction is in reverse bias, the photodiode you operating in the reverse bias. Now, that mode of operation we are calling as photoconductive mode of operation. The photodiode used in this photoconductive mode is more usually reverse bias. the reverse voltage application will increase the depletion layers width. Already people are aware that the reverse, what is happening in the reverse bias, it will increase the width of the depletion region, which in turn decreases the response time and the junction capacitances. This mode is too fast and displays electronic noise. Now ultimately we are this will displace the electronic noise for us. At the same time, it is very fastest mode you have. This is a photoconductor mode. What is the third one? Avalanche diode mode. I already discussed in the last class. What is avalanche effect? Now, avalanche effect, now avalanche mechanism as well as the breakdown mechanism I discussed in the last class. Now, avalanche diodes operate in high reverse bias condition. Now, if you operate higher amount of reverse voltages, then the breakdown occurs. That is you're calling as the avalanche breakdown. Now, yesterday I already discussed, if you are applying the larger reverse bias voltage, now it is in the minus 10 volts or minus 15 volts, at that larger reverse voltages, now what is going to happen? The charge carriers, the free carriers, they are going to be multiplied. Now, due to that multiplication of charge carriers, ultimately the breakdown will occur. That breakdown is avalanche breakdown. Now, what is avalanche diode mode? Avalanche diode is operating in high reverse bias condition. Now, wherever avalanche mode is there, that is in reverse bias with higher reverse voltages. Now, which permits multiplication of an avalanche breakdown to each photo produced electron hole pair. Now, this outcome in an internal gain in the photodiode. Now, which slowly increases the device response. Now, this is for the avalanche diode. Now, we'll see the VI characteristics of photodiode. Now, generally, this is the forward voltage. Now, this is the smaller voltage is the forward voltage, and this is the reverse bias voltage. And now, what is in reverse bias? It is a dark current. It is 1000 lux, 1500 lux, and 2000 lux. That means how much amount of light you are applying on the PN junction. Now, that is illuminance. Now, if you are seeing about the illuminance, that is in lux. You are going to measure in lux. If you are increasing the illuminance, now photodiode is basically a PN junction diode. Now, this is the basic characteristics are looking like this only. In the reverse bias, now depending upon the light, how much you are applying, now according to that, these curves they are going to be takes place. If the more illumination you are applying, the more reverse saturation current you are going to obtain. Now, this is the VI characteristics of your photodiode. Okay. Now we will see the basic things are the same thing. Now, a photodiode, now a photodiode is continuously operate in reverse bias mode generally. Now, the photocurrent is nearly independent of the reverse bias voltage, which is what we are applying. Now, see, for zero illuminance, the photocurrent is almost zero, excluding small dark current. And now I will show you this diagram. For the dark current, for the zero illuminance, if you are not applying any light, approximately it is zero current. Very dark current is going to be flowing through it. And now it is an order of the nanoamperes only. And now see, this is current is in the order of your nanoampere. In the photodiode, now which will convert the light energy into the electrical energy. But in normal PN junction, there is no light energy. Now, due to the applied voltage, the forward bias voltage or reverse bias voltage, the current conduction will take place. In the forward bias, due to the diffusion of majority charge carriers, the current will take place. And the reverse bias, that means the movement of minority charge carriers, a small reverse saturation current will take place. But in case of photodiode, the current is due to the light falling on the PN junction. How much amount of light it is falling on the PN junction? Now, due to that photon energy, they are generating the free carriers in the depletion region. Because of movement of these free carriers, the current conduction will take place. Now, that is the operation of your photodiode. A photodiode will be operating in the reverse bias only. Now, what is the main thing of photodiode? It will convert the electrical energy, the light energy into your electrical energy. Okay. Now, what are the basic applications of our photodiodes? Now, it can be used in electronic devices and smoke sensors. Now, you people are going to see in the smoke sensors. Now, all the hotels are in nowadays in the majority places, people are putting the smoke sensors. If it detects some amount of the smoke, ultimately it will give some alarm. And now in the light sensors, we can applying in the light sensors, and where it is used to measure light intensity in the science and industry. So these are the main applications of your photodiode. Okay, now this is about our photodiode, very only smaller diode we are having. Then now we move on to our next diode, that is nothing but our light emitting diode. Now it is also a small topic. I think people are seeing the practical applications of this light emitting diodes. Now people are seeing the LED. We are calling as LED. LED stands for light emitting diode. Now you see the operation of this LED also here. It is also a very smaller topic for us. Now what is LED stands for? LED stands for your light emitting diode. And now what is the symbol of light emitting diode? I already discussed at the starting of the today's class. If the light arrow mark is, it is inside. If the arrow mark is into the diode symbol, that is your photodiode. This is your photodiode. Now, if the arrow marks are coming out from the junction, that is nothing but your light emitting diode. The name itself, it is saying it is emitting the light. But photodiode is not emitting, it is absorbing the light. Photodiode is absorbing the light so that it is causing the current conduction from P to N region. Now, light emitting diode is, it is emitting in the form of your light. Okay, that's why this is a simple PN junction diode. This is a LED electrical symbol. Arrow marks must be outside. That's a typical LED. People are able to see this. A larger lead is nothing but this. Larger lead is your anode symbol. The smaller one is nothing but cathode. Identification of cathode and anode. If a lead is very larger lead is there, that is anode. Smaller lead is nothing but your cathode. Now, what is a light emitting diode? Now, it is nothing but a device that converts electrical energy into the light energy. Now, previously we have seen what is a device which is converting light energy to electrical energy, that is a photodiode. Now, what is an LED? It is a device which is convert electrical energy into your light energy. Okay. Right. Now, a PN junction diode is that emits the monochromatic light when forward biased, that is nothing but light emitting diode. Now, you people are, I think you people are aware of that. The different color LEDs are there. A red color is there, RGB green is there, blue color LEDs are two color LEDs. Now, the combination of these also, multi-color LEDs also nowadays available. Now, the PN junction diode which emits the monochromatic light when it is in forward bias, that diode we are calling as light emitting diode. A diode which emits the light when it is forward bias, that is a light emitting diode. Now, like the photodiode, I shown you the wavelengths. For the silicon material, if it is having this fixed wavelengths, then only it can absorb the light and the current conduction will take place. Now, like the photodiode, the light emitting diode also, different materials, they are having the different wavelengths. Now, if you are applying that much amount of the thing, then only the particular amount of light is going to be emitted. That may be the red color, that may be green color, or that may be the blue color. Okay, now this is symbol for the LED. I already just now I told you the light emitting diode symbol. Now, always a resistor must be connected in series with the LED. This is a light. This is nothing but your which limits the current. If you are applying 10 volts, now with respect to the resistance is there, the LEDs cannot tolerate the larger voltages, and it can operate for only smaller voltages. If any extra current, high current is coming, that will be limited by the resistance value. Now, it requires generally 1.5 to 4 volts and 10 milliamps to turn on. Now, turn on value, the required voltage to turn on the LED will be very smaller voltages. But if you are applying the 10 volts, the larger voltages, if you are not putting any resistance in series, ultimately this LED is going to damage. Now, one needs to use a resistor to prevent the overloading. To prevent the overloading, now we are going to use a resistor. It must be connected in series with your LED. This is the basic concept. Now, there are two types of LEDs are there. The light emitting diode. One is inorganic LED. Second one is organic LED. That we are calling as OLED. Okay, and nowadays we are seeing the different types of TVs also, and different depending upon the OLED and MOLED. These are the different types of LED techniques. Now we will discuss in the coming slides. Okay, the first one is inorganic LED, and the second type of diode is organic LEDs, OLED. Now, organic LEDs are again they are dividing into two types: the small molecule organic LEDs and the polymer OLEDs, the PLEDs. Now, we are not going in detail about this OLEDs and inorganic and organic LEDs. Just this is a classification of light emitting diodes, but it is not necessary to you people to detail discussion about the inorganic LEDs and the organic LEDs. Okay. And now we'll see. Now, the light emitting diode or LED, as it is more commonly called as LED, it is a specialized type of diode as they have very similar electrical characteristics of PN junction diode. This means an LED will pass current in its forward direction but blocks the current in reverse direction. Now, what is the operation of this? Now, the diode which passes the current in forward bias, which blocks the current in reverse bias, that is a normal PN diode. That means LED is nothing but your normal PN diode. Like the normal PN diode, light emitting diode also will pass the current in forward direction and it will block the flow of current in reverse direction. Okay, now the light emitting diodes are made from a very thin layer of fairly heavily doped semiconductor material, and depending upon the semiconductor material used and the amount of doping, when it is forward biased. Now see, the color of the light, that basically see, the color of the light. Now which color the LED is that is emitting? The color of the light is mainly depending upon the two things. The first thing is nothing but the type of material, and the second thing is what type of material we are using, and the second thing is the amount of doping. Now, it's a doping concentration and the type of material which will result in the color light. That means if it is a red color, green color, blue color, that color of the light is decided by the what type of material you are chosen to design an LED or how much amount of doping you are chosen. These two are important factors to emit a particular type of color from the light emitting diode at the particular wavelength value. Now, when the diode is forward biased, electrons from the semiconductor conduction band recombine with the holes from the valence band. They are releasing sufficient energy to produce photons which emit monochromatic light of the light. Now, previously, what is photodiode? Now, whenever light is falling in the PN junction diode, now light is nothing but it is a photon. It has some sufficient, photons are having sufficient energy. Now, due to this, some charge carriers are going to be generated in the depletion region, movement of that carriers. Now here, what is happening here in the normal light emitting diode, when it is in forward bias, now what is happening? The electrons from the conduction band, the conduction band electrons are there. When electron is falling from conduction band to valence band, now during this time, now what is going to happen? It will release a sufficient energy, which will in the form of your photon. Now, whenever it is releasing energy in the form of photon, photon is nothing but your light energy. It is a monochromatic light energy. Now, what is operation of the light emitting diode? Whenever any electron it is combining any electron from the conduction band to the valency band. During this process, it will emit the photon energy in the form of your light. That is operation of your light emitting diode. Right. When operated in the forward bias direction, light emitting diodes are semiconductor devices that converts electrical energy into light energy. That already I discussed. The construction of LED is very different from that normal diode. Now already I told you, for the normal diode, operation is same, but the construction is different. Now the light emitting diode is a simple p-n junction diode. It is specially doped diode and made up of special type of semiconductor. This topic I already discussed in the previous slide. Now, depending upon the material and depending upon the doping concentration, now the type of the light is going to be decided. And then it emits the light, which when it is in forward bias only, that's why it is called a light emitting diode. Now see the LED characteristics here. What are the LED characteristics? Now the basic characteristics are, take a material. Now already I told you, if the semiconductor material is gallium arsenide material is there, and now the wavelength is nothing but 850 to 940 nanometer. The color is nothing but which color it is going to emit? Infrared IR color it is going to emit. And this forward voltage at the 20 milliamps is 1.2 volts. At this applied positive voltage, and now with this wavelength and this type of material is emitting a light of color infrared IR. Now, if it is a gallium arsenide phosphate, this is a material type. Now, with a wavelength of 630 to 660 nanometer, now which color it will emit? That is a red color. Okay, it is a 1.8 volts, operating voltage is 1.8 volts. Now, like this is a material, gallium arsenide phosphate, same material with the different wavelengths and with the different operating voltages. Now, it is generating the different types of color. And for the yellow, it is gallium arsenide phosphate with the nitrogen. With the wavelength is, this is a wavelength. The emitted color is yellow with operating voltage is 2.2 volts. Now this is the simple characteristics of your light emitting diodes. Now main thing, the color of the light, that will depends upon the three factors. The first one is the type of material you are using. The second one is a wavelength at the same time, and third one is a doping. These three main reasons on which color the LED is going to emit. Okay, how does the LED is going to work? How LED is going to work here? Now we'll see the basic operation of this LED. Now, the light emitting diode, simply a PN diode. When the diode is forward biased, then the electrons and holes are moving fast across the junction. Now that is a basic procedure. Now if it is a forward bias, when you are applying the positive voltage to P type, that is a negative voltage to N type, that is a forward bias connection. What is going to happen in forward bias? Majority charge carriers, they will diffuse through the junction. That means electron will move to the P side, holes will move to the N type, that the maximum current flow will take place. Okay, and they are recombining constantly. They're removing one another out. Now what it is recombination? The N type electron is crossing the junction. It is coming to the P type. It is recombining with the hole. And from the P side, if a hole is moving from the P to the N type, and some of the holes they may recombine with electrons in the N type. Now this is what is going to happen. Soon after, the electrons are moving from the N type to the P type silicon. It combines with the holes, then it disappears. Now what will happen? If the electron is moved to this type, moved to the P side material, P side region, it is recombined with the hole. After recombining with the hole, immediately this electron will disappear. After recombination will takes place, what is going to happen? Electron is going to be disappear because the recombination takes place. Hence, it makes the complete atom and more stable, and it gives the little burst of energy in the form of tiny packet of photon of light. Now, whenever an electron is recombined with the whole, now immediately the electron will disappear. Now it will make a stronger atom. It is a complete atom and a stable atom. Now, during this process, it will give us a small little burst of energy that is in the form of tiny packets. That is in the form of your photon of light. That light is nothing but it is emitting the light in the form of your light. This is the basic working operation of your light emitting diode. The same thing I kept here. The working principle of LED is based on the quantum theory. What the quantum theory says? The quantum theory says that when electron comes down from the higher energy level to lower energy level, then the energy emits in the form of photon. This is a basic quantum theory. I think people are aware of this basic quantum theory. Okay. Now, the photon energy is equal to the energy gap between the two energy levels. If the PN junction diode is in the forward bias, then the current flows through the diode. Ultimately, this is a basic concept. The flow of current in the semiconductor is caused by the both flow of holes in opposite direction of the electrons. Hence, there will be recombination. I think last slide what I said that I'm elaborating in this present slide. That due to the flow of the charge carriers. Now, whenever the recombination indicates that the electron in the conduction band, the jump down to the valence band. Actually, the recombination meaning is electrons will be there in the conduction band. Now they are jumped to the valence band. Now, when the electron jump from one band to another band, the energy in the form of your photon, now that is exactly equivalent to the forbidden energy gap. Now, this is the basic working principle of your light emitting diode. Now, see this is a simple operation. What is happening when you are applying the in the forward bias condition? Now, this hole is moving to this side because in the forward bias, the diffusion of charge carriers will take place. The electrons will move to the p type. Now, whenever their recombination takes place, that is, it will give a small amount of energy in the form of your photon. That photon of energy it is going to emit it to the outside. Now, this is the basic working principle of your light emitting diode. Now, these are the basic VI characteristics of your LED. What is the VI characteristics of LED? The current versus voltage characteristics. It is a simple PN junction diode. It is operating in forward bias. What is the forward bias characteristics of PN junction diode? If it is more than the cut-in voltage, then the current will start increasing. This is a forward bias characteristics of PN junction diode. Now, here depending upon the applied voltage. Now, for the infrared voltage, that is 1.8 volts is there. Now, red is, I already shown you in the table. For the red, amber, yellow, green, blue, white. Now, with the different applied voltages, the characteristics curves will be looks like this. For the IR, if it is IR, now this is immediately the voltage is very, very small. Now, for red is next applied voltage. Now, I will show you that side also. Now, this is a value. At the 1.2 volts, the current will start conduction. The light will emit from the gallium arsenide device for the IR color. If at the 1.8 volts, the color is a red color. At the 2 volts, that is amber color. At 2.2, yellow, and the green as well as the white is also there. These are the values. That's why first one is the smaller voltages, that is IR light. Second one is red. Third one is amber. Next yellow, green, blue, and white. See, if you take the white characteristics also, it is like a normal PN junction forward biased characteristics. That's why LED characteristics are nothing but your simple PN junction diode VI characteristics. Okay, this is anode and cathode. This is a conventional current flow. And now this is emitting the light in the form of your packets, that is the photons. Now this is a simple VI characteristics of your light emitting diode. That's it. Now these are the small topics. That is nothing but your photodiode as well as a light emitting diode. Now once again, in brief, I am telling now what is a photodiode as well as a light emitting diode. Just I am telling. Photodiode is a type of diode. Yeah. Just I am summarizing the today's one. The today's topic, that is the photodiode as well as the light emitting diode. Now, what is a photodiode? The photodiode is, it is one form of your PN diode, but it is going to operate in your reverse bias condition. Now, the photodiode can be operated in the three modes of operation. Now, what is basically the function of photodiode? The the photodiode is, it will convert the light energy, the electrical energy. That is the basic function of your photodiode. Now, photodiode can be operating in the three modes. The first one is photovoltaic mode, and the second one is a photoconductive mode, and third one is nothing but avalanche diode. What is photovoltaic mode? Photovoltaic mode is nothing but the zero bias mode. If you are not applying anything at the P and the cathode, that mode of operation is called photovoltaic mode. Now, how the energy is going to be generated at the same time, how the current and the voltage is going to be flow in the photovoltaic mode? Now, due to the presence of light. Now, the current, amount of current, that is completely due to your how much amount of light it is falling on the PN junction. That is for the photovoltaic mode. Now, what is photoconductive mode? In the photoconductive mode, it is operating in the reverse bias configuration. During the reverse bias, if you are applying the reverse voltage, smaller reverse voltages, according to that, it is going to operate. The third one is avalanche diode. What is that avalanche diode? Which will convert now electrical energy into the light energy. Now, that is quite opposite to your simple photodiode as well as your light emitting diode. Now, these are very simple diodes. Now, you can easily get the full clarity about the diodes at the end of the today's class. I will share the today's PPT also to your everyday class presentations people are receiving through your CRs, because on the same day I am sending the presentation to your class CRs. Okay, and now one of your people asked me about the tunnel diodes, and the last class my voice was broken in the tunnel diode. Just briefly, I will explain the tunnel diode operation in this 10 minutes time, because by 3:40 I will stop the today's class. Now we will start the quiz at the 3:40. Right. Now this is the, what I discussed in the last class. Now what is a tunnel diode? It is other name of tunnel diode is Isaki diode. And now Isaki is Leo Isaki is the scientist name who proposed a tunnel diode. The main thing, main difference between PN junction diode Zener diode and tunnel diode is the doping concentration. Okay. Now, in case of normal PN junction diode, that is the doping concentration is 1 part for 10 power 8. Now, in case of Zener diode, 1 part of impurity you are adding for 10 power 5. Now, in case of tunnel diode, heavy doping, that means 1 part for 10 power 3 1. Now, that is for your uh, tunnel diode. Now, at the same time, the width of the depletion region is very, very small. Now, it is generally made up of germanium and gallium arsenide. It shows the tunneling phenomenon. Now, we'll explain you the same thing. If this slide is clear, the complete tunnel diode is going to be clear. Now, see here, the width of the depletion region will depends upon the doping concentration. The Na is the doping concentration. That means, if the doping concentration is high, the width of the depletion region is very, very narrow. In the sense, it is very thin. Now, if the width of the depletion region is very thin, now what it can do? The charge carriers, they can diffuse at the same diffuse the tunnel from one region to another region. Now, see the concept. Now, the width of the depletion junction barrier varies inversely as a square root of the impurity concentration. In the tunnel diode, what is happening? By increasing impurity concentration, the width can be reduced to 5 micro to 0.1 micro. That means very thin junction is there. Okay, according to classical mechanics, a particle can possess, what it can possess a particle? The potential which is at least or equal to greater than, then only the current will take place. Now, what is the meaning of this? If you take a simple PN junction diode, a small PN junction is there. In this junction, some barrier potential is there, 0.7 volts. If you apply more than the barrier potential, then only the diffusion of charge carriers will take place, the current conduction will take place. This is for general. But if the width of the depletion region is very, very thin, now that means that is approximately 0.01 micro. According to Schrodinger equation, what it means, there is a probability of electron to penetrate into one region to another region. See, I will tell you the simple difference between penetration and the diffusion. What is the meaning of diffusion? Now I will take the band diagram. This is a conduction band and this is your valency band. This is I'm taking the N-type material. If it is a conduction band, it is a valency band. This is for your P-type material. If electron from the conduction band, it is moving into the other side of the conduction band, that is a diffusion. Remember this. If any electron is moving from the conduction band of N region to conduction band of P region, is a diffusion. What is the tunneling? If any electron from the conduction band, if it is entering into this valency band, now that is a tunneling phenomenon. Tunneling is nothing but it is penetrating that electron into the other side of the other band, that is not the conduction band. Now, according to Schrodinger equation, if the width of the depletion region is very thin, now there may be a possibility of penetrating the electrons into the other side. Now, the penetration is nothing but the tunneling. There is a tunnel between conduction band of the N region to the valency band of your P region. That's why in the tunnel diode, 3 types of currents is going to take place. Now I am going to direct you to this. See the energy band diagram. This is normally for N type and this is for P type. See the Fermi level. Now this is, now you may get one out, sir, why the structure will, band bending structure will be like this only? Now this structure is came based on the doping concentration. Because of heavy concentration, it is going to be looks like this. Okay. Now what is going to happen? See, now this is a conduction band. Here electrons are there. Now in this valency band, now here what are there? Holes are there. This is a valency band. Holes will present here. Conduction band, electrons are there. According to Fermi level, these two will be exactly opposite to each other. Now at the zero bias, see, now there is this much amount of portion is that this is very opposite to conduction band of electrons or opposite to valency band. Here holes, empty holes are there. These electrons, they can tunnel into this. See, this is a conduction band of your P type. If the electron is coming from here to here, that is a diffusion. But at the smaller forward voltage also, some electrons, they are tunneling into the other side. Now this current, at this zero bias, now there is no movement of this. With the smaller forward voltage, if you are applying very small forward voltage, now see this is a gap you are having, this is small gap is there. Electrons from this side, they can tunnel into the p side of valency band. Now that's why the small amount of current is there. Now see here, I'm not applying the more than 0.7. So more than 0.7 you're applying, that is more than barrier potential. The current is due to diffusion. But here applied only small forward voltage, that is only 0.1 volt. For the 0.1 volt also, there is a current flow in the tunnel diode. That current flow is due to tunneling of the electron. Now, still if you apply the little bit more voltage, that is I am going for some 0.5 volts. At the 0.5 volts, this conduction band is going to the upside, this valence band is coming down. At this case, maximum amount of place is at exactly opposite side, so that some of the electrons, they can, more number of electrons, they can tunnel into the valency band of p type. That's why maximum amount of tunnel current, this current is a tunnel current, will occur, which is less than 0.7 only, less than barrier potential. Less than barrier potential, the current, there is a current flow in the tunnel diode. That current flow is due to your tunneling of charge carriers, the electron. Now, still if you are increasing, and now what is going to happen if you are going for the 0.6 volts? Now this band is, conduction band is moving upside, valence band is coming down, so that very small amount of electrons they will tunnel. Once again, the current flow is going to be less. Now, if it is greater than 0.7 volts for the larger forward bias voltage, now once again it will come down. Forward bias operation will take. What is the forward bias? Now it is greater than the 0.7. Now this will come to here. Now diffusion of charge carriers will take place. Now see, this is the case. Now this is the maximum case for the tunnel case. At the higher forward voltages, now see, this is not exactly equivalent to this case. Now here this is a valency band, and here the conduction band. Tunneling is not possible here. Now what is going to happen? The diffusion of charge carriers will take place. If it is greater than the 0.7 volts, greater than 0.7 volts, operation of tunnel diode is like a PN junction diode. It is going to be increased like this. Below the barrier potential, initially it has a higher tunnel current. Later it will tunnel current will reduce, and then it will follow the forward bias characteristics of the normal PN junction diode. Now this is the case. In the reverse bias case, the normal case, the forward bias electrons are tunneling into this side. The reverse bias holes will tunnel into this side. Okay, this is a simple operation of your tunnel diode. Just go through the presentation, and you people will get the clarity about the tunnel diode. Okay, I hope this is the simple revision of your tunnel diode, what I discussed in the last class. Now almost we came to the end of the today's session. Now we will start the quiz for the today's session. It is almost 12:42 is there. And now I am starting the today's quiz. All of you take the quiz. And now only 10 MCQs are there. Mostly it may take only 10 to 15 minutes. Now we are giving you the sufficient time, the 20 minutes time. Those are completed early, and now you people will get the a longer break time. Now if you are completing within 10 minutes, so that you will get the 20 minutes break time. Okay. Now we are starting the test. Now all of you take the test.